All right, functions in trigonometry, final exam review, video number 7. Okay, we are on this problem of the non-calculator section. Okay, we're talking about the inverse functions. I'm going to say a few words about inverses in trigonometry. First of all, do not confuse inverse with reciprocal. Now, I know when you see this exponent -1, you think reciprocal. And but the reciprocal of cosine is secant, which is a different thing. What we are, this is a true inverse. And what is an inverse in functions? I switch the x and the y value. So normally I put in an x value, you give me a y value. Now what's the inverse? I give you a y value, you back calculate the x value. In other words, this is saying that what angle will give me a cosine of -√3 over 2. Well, I need to go to my unit circle. What angle has a cosine of -√3 over 2? Well, I see there's two angles. There's 7 pi over 6, and there's 5 pi over 6. Well, which one do I choose? Well, I had to remember that the domain of the inverse cosine function is, I like to teach my students, it's the top half of the unit circle. Okay, for the sine, it is the right half of the unit circle. Okay, so we throw this guy out because he is outside that domain. So here's our answer. Okay, a lot of this, remember back to logarithms. Logarithms are inverses of the exponential function. And what's an inverse? Well, it means, I switch the x and the y. So what I did is I converted this logarithmic function to an exponential function, and then it's fairly easy to solve. 27 raised to the what power will give me 3. Well, the cube root of 27 is 3. How do I write the cube root as a rational expression? That is just an exponent of 1/3. Okay, this one is super easy. This guy and this guy, these are inverses of each other. And you can also think if I do an operation on my inverse, I'm back where I started. So if I take 8 and use it as an exponent of e and then take the natural log of that, I just undid what I did. All right, so these are inverses, so what happens then is the answer is just simply 8. Okay, it's kind of like, all right, if I take a number and multiply it by 5, and then what's the inverse of multiplication? It's division, so I just undo what I did. You might want to think of it that way. All right, I did the same thing on this problem as I did on this problem. Once I convert it to exponential format, it is easy. So what exponent always yields a value of 1? Exponent of 0. Same drill. And also, no, we'll just leave it at this argument. Okay, so what value of exponent will yield the argument? 1. All right. Very sort of similar problem to this. Okay, we're going to approach it the same way. However, this is not on my unit circle. So I can't actually get a value of theta. All I can do is I can get the trig function for theta. I can define theta in terms of sine, cosine, and tangent. This is what I mean. All right, so where did I get this little triangle from? Well, first of all, I'm in first quadrant and positive. All right, so I know that the inverse sine is only defined in first and second quadrant. And since this is positive, I'm in first quadrant. That's why I drew it in first quadrant. Okay, well, what is this? This is the side opposite. This is the side adjacent of some angle theta in the first quadrant. So I set it up here. I set up my sketch. All right, and then I use Pythagorean. solve for my side adjacent. Okay, so now I have a full triangle. I know what theta is. Okay, so then it asks for then the cosine of my angle theta. Okay, just like, yeah, it's not a very good argument. All right, let's go back to this. Okay, so what is the cosine of this angle? Well, the cosine of the angle is adjacent over hypotenuse, 3/5. Done. That's not on my unit circle. That's not on my unit circle. But when I subtract the two, that is on my unit circle. So that was my hint to do that rather than try to go to my summation formulas, because these guys don't exist on the unit circle. This guy does. All this half angle, double angle, angle sum, you know, it's no good to us if the angles that we're working with are not on the unit circle. Okay, cosine 240, look at the x-coordinate of angle 240 on a unit circle, -1/2, and good to go. All right, so problem number 11. Okay, we're going to attack that just like we attacked this. Okay, quadrant 1. Okay, this is going to be my side opposite. This is going to be my hypotenuse. All right, how am I going to set that up? Well, I'm going to draw my angle theta. Again, that's not on my unit circle. So I'm going to have to define theta in terms of ratio of sides, either sine, cosine, or tangent. All right, so I'm given this data, a little bit of Pythagorean here. Now I've got my full triangle. Okay, now I'm ready to do the double angle formula. Okay, this is theta, and there's like 3 different versions of the double angle formula. I mean, this is either one of them work. This is kind of my personal favorite. What is the cosine of the angle? Well, it is adjacent over a hypotenuse squared, sine, already given. Right? So that's your trig. The rest is math. Got a common denominator. Can't simplify. Done. All right, 12. Want the equation of the asymptotes. And this is obviously hyperbola. There's an easy way to do this, and there's a hard way to do this. Some folks, they just want to work straight in formulas. You know, they go, well, which one of these is my a squared? Which one of these is my b squared? And I have all these plug and chug and stuff like that. If you like to do that, good for you. Okay, I can't. I have to draw a picture. All right, so I know then my x squared is my positive term. So this is going to have a horizontal orientation, which means my a squared will be the denominator of x, because that is the positive term. Quite a bit different than the ellipse on how I decide a squared and b squared. So by default, b squared is then 36. Okay, now how does that help me? Remember what a and b are. They're kind of the dimensions of this imaginary box for plotting the hyperbola. That imaginary box fixes my ability to draw in the asymptotes. Okay, and then if I actually had to draw the function, this edge of the box here would then be a vertex. Okay, and then I would sketch that in, and then I know for a hyperbola, c squared is equal to a squared plus b squared. Again, notice this is a little bit different than what we have for ellipse, and then the foci is going to lie somewhere inside here on the vertex. All right. What I have here is, because I've drawn this little box, I know what that side of the box is. It's 6. I know what this side of the box is. It's 3. Oh, that is rise over run. So this asymptote has a slope of positive 2. This slope has a asymptote of -2. Again, from a graph, y equals mx plus b. What's the equation of that line? Well, very simple. Okay, it goes through the origin. So y is equal to mx plus b. Okay, there's your equation. Do you need to write the 0? No, you don't. There you go. There's your equations of the asymptotes. Got one more. Let's do this. Graph the ellipse. Okay, well, let's look at the equation. What do we have? First of all, we have the coordinates of the center. -2, +2. How do I know that? This guy, this guy. Change their signs. That's the x and y coordinate. All right, I know it's an ellipse. Which one is the bigger number? 9 is the bigger number. So a squared is equal to 9. That means a is equal to 3. Okay, by default, b squared is equal to 4. Therefore, b is equal to 2. This is all the information I need to make the graph. First, let's plot the center. Plot the center. I know it's a horizontal orientation. How do I know that? I know that because the bigger number, a squared, is underneath the horizontal variable x. All right, so plot this. My major axis is 3 units long this way, 3 units long that way, for a total major axis of 6. 2, 2. Draw your little squished egg thingy here, and you are done.